In the quiet stillness of space, where time unfolds across billions of years, a new eye has opened, an eye that peers deeper into the cosmos than ever before. This is the story of the James Webb Space Telescope, a marvel of human ingenuity and collaboration built to explore the most distant corners of the universe. Launched in December of 2021, the James Webb Space Telescope, often called JWST, is the most powerful space observatory ever created. Developed through a partnership between NASA, the European Space Agency, and the Canadian Space Agency, this extraordinary instrument was decades in the making. Its journey through the stars has just begun, but already it has started to transform how we see the cosmos. Unlike its predecessor, the Hubble Space Telescope, which primarily observes invisible and ultraviolet light, JWST is tuned to the infrared spectrum. This allows it to see what no other telescope can: the faint ancient light of galaxies formed just a few 100 million years after the Big Bang. With its gold-plated 6.5-meter primary mirror and its tennis court-sized sun shield to protect it from the heat of the sun, JWST is built to be extremely sensitive and precise. Its mission is as ambitious as it is inspiring: to observe the first galaxies and stars that lit up the universe, to explore the atmospheres of distant exoplanets, and to answer questions that have puzzled scientists for generations. What did the first light in the universe look like? What are the origins of stars and planets? Could there be life beyond Earth? As we begin this journey together, through vast fields of stars and glowing clouds of dust, let the calm beauty of discovery accompany you. In the silence of deep space, among the galaxies and nebulae, answers are waiting to be found. And now we begin to uncover them. Chapter 1: The Dawn of a New Era. The James Webb Space Telescope represents more than just a technological achievement. It marks the beginning of a new era in astronomy. For centuries, we have looked to the skies with curiosity. Now, with JWST, we do so with new clarity, armed with tools that allow us to glimpse the secrets of the cosmos with unprecedented precision. JWST's infrared vision is at the heart of this new era. Infrared light, unlike visible light, can pass through dust clouds and gas that would otherwise obscure our view. This makes JWST ideal for observing the early universe, where the first stars and galaxies formed. These ancient objects are so distant that their light has been stretched into the infrared over billions of years, a phenomenon known as redshift. To detect this light, a telescope must be both cold and sensitive. JWST, stationed at the L2 Lagrange point, about 1.5 million kilometers from Earth, remains shielded from the sun's warmth and perfectly poised to see the faintest glimmers of creation. Its sun shield, made of 5 ultra-thin layers of a material called Kapton, keeps the telescope at temperatures colder than 220 degrees Celsius. This cooling is essential for capturing the heat signatures of distant galaxies and newborn stars. Every part of JWST is engineered for precision. From its segmented mirror that unfolds like a golden flower in space, to its suite of scientific instruments that decode light into data. But what truly makes JWST revolutionary is not just its design, but its purpose. It was built to answer the most profound questions. how did the universe begin? How do stars and galaxies evolve? Could life exist on other planets? In its first months of operation, JWST has already delivered breathtaking images, detailed views of nebulae where stars are born, galaxies in collision, and clusters of ancient starlight. Each image is a window into time, a story written in light that has traveled billions of years to reach us. We are now living in a moment that future generations will look back upon as transformative. The data we gather today will shape science for decades. JWST is not just looking at the universe, it's rewriting how we understand it. And this, truly, is the dawn of a new era. Chapter 2. Peering into the early universe. Imagine looking so far into the cosmos that the light reaching you began its journey over 13 billion years ago. With the James Webb Space Telescope, this is no longer imagination. It is reality. JWST has become our time machine, allowing us to peer into the earliest moments of the universe's life. When we look into the night sky, we're not seeing objects as they are now, but as they were when their light began traveling to us. The farther away a galaxy is, the further back in time we are seeing. Thanks to its powerful infrared capabilities, JWST captures this ancient light with extraordinary clarity. In just its first months of operation, the telescope unveiled some of the most distant galaxies ever observed. Some formed a mere few 100 million years after the Big Bang. Among these discoveries was a tiny red dot in the deep field image known as GLASS Z13, a galaxy so far away that it shattered previous distance records. What we see in the image is light that has traveled over 13.4 billion years to reach us. This means JWST is witnessing galaxies as they existed when the universe was still in its cosmic infancy. These ancient galaxies look nothing like the grand spirals we're familiar with today. Instead, they are compact, chaotic, and filled with hot, young stars. Their shapes are irregular, like cosmic building blocks still finding their form. JWST helps scientists study how these first galaxies assembled over time, how they merged, evolved, and gave birth to the large structured systems we see today. But JWST doesn't just show us what's out there. It challenges our expectations. Some of the earliest galaxies appear to be more massive and mature than models predicted, suggesting that star formation and galactic growth began even earlier than we once believed. This has prompted scientists to revisit long-standing theories about how the universe evolved in its first billion years. These revelations are more than just stunning visuals. They are clues to our own origins. Everything we see today, from galaxies to stars to planets and people, began in that distant, mysterious past. By studying it, we get closer to understanding where we came from and how the cosmos came to be the way it is. As we continue to explore the early universe, JWST opens a window not only into ancient light, but into timeless wonder. With every image, we are reminded of how small we are and how connected we are to the grand tapestry of the universe. Chapter 3. Unveiling Starbirth and Death. Among the most breathtaking gifts of the cosmos are the places where stars are born and where they meet their end. With the James Webb Space Telescope, we are now witnessing these dramatic cosmic processes in exquisite detail. offering insights that once seemed unreachable. Deep within giant clouds of dust and gas, stars begin their journey. These vast nurseries, called nebulae, have long fascinated astronomers. But until now, much of their inner workings were hidden from view. Dust blocks visible light, making it nearly impossible for traditional telescopes to see what lies within. That is where JWST's infrared vision becomes revolutionary. It can pierce through those dusty veils and reveal what is happening inside. Tiny clusters of young stars, glowing cocoons where stellar embryos grow, and jets of gas being ejected as stars ignite their nuclear furnaces. One such image comes from the famous Carina Nebula, a stellar nursery located about 7,600 light-years from Earth. JWST captured towering walls of dust, shaped like mountains, illuminated by newly forming stars. These breathtaking structures are not just beautiful, they are active, dynamic regions where stars are literally coming to life. But stars, like all things, do not live forever. When a star exhausts its nuclear fuel, its fate depends on its size. Smaller stars quietly fade into white dwarfs, while massive ones end in spectacular supernova explosions. These violent deaths scatter elements like carbon, oxygen, and iron into space, the very ingredients of planets and life. JWST has also turned its gaze toward the Southern Ring Nebula, the glowing remains of a dying star. Its infrared images show layers of expelled gas expanding into space, rich in complex molecules. What was once a living star now becomes part of the next generation. Its elements recycled into new stars, new planets, and possibly new life. This cycle of birth and death is not just poetic, it's essential. Every atom in your body, every breath you take, and every rock on Earth was forged in the heart of a star or in the wake of its explosion. By studying these processes, JWST helps us understand our own cosmic ancestry. Through its lens, we see the universe as a living, evolving system, where death gives way to rebirth, and where beauty and destruction dance in eternal balance. The silence of space among clouds of gas and fading light. The story of creation continues. Chapter 4: Exoplanet Exploration. Beyond the borders of our solar system, orbiting distant stars, lie countless worlds known as exoplanets. For decades, scientists have dreamed of not only finding these alien planets, but also understanding what they are made of, what they look like, and whether they might harbor life. Thanks to the James Webb Space Telescope, that dream is becoming a reality. Webb's infrared capabilities allow it to peer into the atmospheres of exoplanets, something no other telescope has done with such precision. When a planet passes in front of its star, a portion of the starlight filters through its atmosphere. By analyzing that light, JWST can detect the chemical fingerprints of gases like water vapor, carbon dioxide, methane, and even ammonia. One of the telescope's early triumphs came with its observation of WSP 96b, a hot gas giant located about 150 light-years from Earth. Webb not only confirmed the presence of water vapor in its atmosphere, but also detected haze and clouds, features previously unseen in such detail. Though not a habitable world, it was a proof of concept. JWST could read the skies of alien planets. But the real excitement lies with rocky exoplanets, planets similar in size and composition to Earth. Webb is targeting several of these, such as the TRAPPIST-1 system, a cluster of 7 Earth-sized planets orbiting a red dwarf star only 40 light-years away. Some of these planets lie in the so-called habitable zone, where temperatures might allow liquid water to exist. Webb's observations of the TRAPPIST-1 planets are ongoing, but early data is promising. By detecting molecules like carbon dioxide and methane, scientists hope to understand whether these worlds have thick atmospheres, oceans, or even signs of biological activity. The search for life beyond Earth has always captured human imagination. With JWST, that search has shifted from speculation to data. Each new spectrum, each new chemical trace, brings us closer to understanding our place in the universe. But beyond the quest for habitability, studying exoplanets expands our understanding of planetary diversity. We now know of lava worlds with molten surfaces, gas giants that orbit their stars in just days, and ocean planets that may be entirely covered in water. These discoveries challenge our assumptions and remind us that our solar system is just one arrangement among many. As the telescope continues its mission, it will uncover more of these distant worlds, some strange, some familiar, and perhaps one day, one that reminds us of home. Chapter 5. The Future of Astronomy. The James Webb Space Telescope has already reshaped the way we explore the universe. But its journey is just beginning. With each image it sends back, with every spectrum it decodes, Webb is laying the groundwork for a new era in astronomy. One marked not by limitations, but by possibilities. Scientists believe JWST will continue to make groundbreaking discoveries for at least a decade, perhaps much longer. Unlike telescopes limited by visible light, Webb's infrared vision opens doors to observing the coolest and most distant parts of the cosmos. It can peer into the dust-shrouded regions where stars are born, study the faint glow of ancient galaxies, and detect the heat signatures of exoplanets many light-years away. Future observations will dive even deeper into cosmic history, searching for the first light that ever existed. Stars and galaxies born just a few 100 million years after the Big Bang. By comparing what Webb sees with what we know from older telescopes like Hubble, scientists can map out the universe's timeline with greater clarity. JWST is also expected to help unravel long-standing mysteries. What is dark matter made of? How fast is the universe really expanding? Could there be entirely new forms of matter or physics we have yet to imagine? Webb's data may not answer all these questions, but it will narrow the field and guide future research. Its impact extends beyond science. The breathtaking images, stellar nurseries that look like paintings, galaxies shaped like spirals, arcs, and jewels, have inspired people of all ages. These views serve as reminders of both the enormity and the beauty of the universe, stirring curiosity and wonder in anyone who sees them. Educational institutions, museums, classrooms, and even living rooms now display JWST's discoveries. Children dream of becoming scientists, artists draw inspiration, and everyday people looking up at the stars feel a little closer to the mysteries above. The legacy of the James Webb Space Telescope will be measured not just in data, or publications, but in the countless minds it influences. It is a bridge from past to future, from questions to answers, from Earth to the stars. In the years to come, Webb will not be alone. It will work alongside other space missions, ground-based observatories, and future telescopes still on the drawing board. Together, they will build a richer, more detailed understanding of our cosmos. But for now, in the quiet of deep space, Webb continues its watch, steady, patient, and brilliant, unlocking secrets, one photon at a time. Chapter 6: Galaxies Beyond Imagination. Revealing the unexpected architecture of the universe. When we look into the night sky, we see specks of light, some stars, some planets, and hidden among them, distant galaxies. But what the James Webb Space Telescope has revealed goes far beyond what our eyes could ever detect. Webb's deep field observations have opened windows into the ancient past, unveiling a multitude of galaxies that defy our previous understanding. One of JWST's earliest and most profound accomplishments was the release of deep field images, such as the now iconic SMACS JO723. In this single frame, taken over just 12.5 hours, the telescope captured thousands of galaxies, each one a swirling island of stars, gas, dust, and dark matter. Some of the light captured in that image had traveled over 13 billion years to reach us, a silent journey through time and space. Among these galaxies are some of the earliest ever observed, forming just a few 100 million years after the Big Bang. Their presence so early in the universe's history stunned astronomers. Many of these young galaxies appear brighter, more compact, and more numerous than expected, leading scientists to question long-held models of galactic evolution. Why were so many galaxies already formed so quickly? And why do they appear so different from what simulations had predicted? Even more intriguing, JWST has identified ultra-red galaxies that seem to contain massive amounts of dust, a substance thought to be produced primarily by mature stars or supernovae. Yet here they are, in the early universe, already rich in dust, suggesting that star formation and death may have occurred far more rapidly than we imagined. Webb has also revealed galaxies with bizarre and distorted shapes. Some look like stringy filaments, others like chaotic blobs. These irregular forms likely result from frequent mergers and gravitational interactions in the early cosmos. What we're witnessing is a young universe still finding its structure, still building the grand spirals and ellipticals we're more familiar with today. In some cases, JWST has captured galaxies in the midst of collisions. Two or more galaxies merging, their arms twisted and contorted by immense gravitational forces. These cosmic dances are not destructive in the way we might think. Instead, they can ignite waves of star formation and lead to the creation of even larger galactic systems. But the surprises don't end there. In a galaxy cluster known as El Gordo, JWST detected signs of gravitational lensing, a phenomenon where the massive gravity of the cluster bends light from galaxies behind it, magnifying and stretching their images into arcs and halos. These cosmic lenses not only create stunning visuals, but also allow astronomers to peer even farther into the past by amplifying faint light from galaxies that would otherwise be invisible. The telescope has also begun to uncover something even more elusive: dark galaxies. These are thought to be galaxies with very few stars, made mostly of dark matter and gas. Though nearly invisible, their gravitational effects can be measured, and JWST's sensitivity may soon allow us to confirm their existence, helping to solve one of cosmology's greatest mysteries. Together, these discoveries paint a portrait of a universe that is not static or uniform, but dynamic, chaotic, and rich with diversity. Galaxies are born in fire and dust, grow through collision and fusion, and evolve into the vast and elegant systems we see today. JWST is not just showing us where galaxies are, it's revealing how they live, change, and relate to the grand architecture of the cosmos. And with every image, it reminds us that the universe is far stranger and more beautiful than we ever dared to imagine. Chapter 7: Cosmic Clocks: Measuring the Age of the Universe. Unlocking time with light and space-time in the cosmos is not measured with ticking hands or digital displays. Instead, it's written in light that has traveled for billions of years to reach us, carrying with it the story of the universe's distant past. With the James Webb Space Telescope, scientists now possess a cosmic time machine more precise and revealing than any before it. But how do we measure the age of the universe? And how does JWST help refine that measurement? It begins with the cosmic microwave background, the faint afterglow of the Big Bang, which tells us that the universe is roughly 13.8 billion years old. But Webb doesn't look at the microwave background. It specializes in infrared. What it can do is detect the oldest and faintest galaxies, whose light has been stretched and shifted by cosmic expansion. These redshifted galaxies act as time markers, showing us what the universe looked like when it was just a few 100 million years old. ST's ability to detect these ancient galaxies helps astronomers build a more detailed timeline of cosmic evolution. One surprising finding has been how quickly galaxies appeared and matured after the Big Bang. This has implications for our understanding of cosmic time. It means that star formation, black hole growth, and chemical enrichment happened on much faster scales than previously believed. In a sense, JWST is recalibrating our cosmic clock, but that's not all. The telescope also plays a role in refining one of astronomy's most debated measurements: the Hubble constant, the rate at which the universe is expanding. This number is crucial because it links distance and time. Yet, two methods for calculating it, one based on the early universe and another using nearby galaxies, give slightly different results. ST helps bridge this gap by observing so-called standard candles like Cepheid variable stars and Type Ia supernovae, objects whose intrinsic brightness is known. By comparing their true brightness with how dim they appear from Earth, scientists can calculate precise distances. These measurements, in turn, help determine how fast the universe is expanding. The more precise our distance ladder becomes, the closer we come to resolving the Hubble tension, a mystery that could lead to new physics or reveal deeper truths about the structure of the cosmos. There's another way JWST is helping us track cosmic time: by analyzing stellar populations within distant galaxies. Older stars, particularly red giants and white dwarfs, serve as indicators of a galaxy's age. By studying their light spectra, astronomers can estimate when the first stars formed in that galaxy, placing it on the universal timeline. Even the chemical fingerprints left in galaxies, such as the abundance of elements like carbon, oxygen, and iron, reveal clues about age. The heavier the elements, the more generations of stars must have lived and died to create them. This cosmic alchemy allows scientists to estimate how long a galaxy has been building its stellar population. JWST's detailed infrared spectra bring all these indicators into focus. With it, we are building a layered and refined portrait of the universe's chronology, from the flash of creation to the quiet glow of ancient stars. It's remarkable to think every photon we detect is a messenger from the past. Some come from a few thousand years ago, others from billions, and together they let us trace the heartbeat of the cosmos, ticking softly in the dark. With the James Webb Space Telescope, we're not just observing the universe, we're reading its clockwork. Chapter 8: Black Holes Unveiled. The dark hearts of galaxies, peering into the shadows of the universe. They are invisible yet immense, silent yet unimaginably powerful. Black holes, those mysterious objects where gravity is so strong that neither even light can escape, have long been shrouded in mystery. For decades we've observed their influence indirectly, the way they warp space, stir stars, and fuel the centers of galaxies. But with the James Webb Space Telescope, the veils are slowly being drawn back. What makes JWST so valuable in studying black holes is its infrared vision, which allows it to peer through clouds of gas and dust that often surround these enigmatic giants. Unlike visible light telescopes, which are blinded by these obstructions, Webb sees the subtle glow of material swirling into black holes, revealing their structure, their feeding habits, and their role in shaping the cosmos. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, millions or even billions of times more massive than our Sun. For years, we knew they existed, but their formation remained a puzzle. Were they born as small seeds in the early universe, gradually growing over time? Or did some emerge suddenly, already massive, just a few 100 million years after the Big Bang? JWST is now offering clues. By observing extremely distant quasars, super bright objects powered by black holes actively consuming matter, JWST has spotted fully formed supermassive black holes just 600 to 700 million years after the universe began. This is astonishing. It means these cosmic giants must have grown much faster than expected. Or perhaps the first black holes were born massive to begin with. Either way, Webb is pushing our understanding into new territory, but it doesn't just study the distant past. Closer to home, JWST also examines intermediate mass black holes, those that are harder to detect because they sit between stellar mass and supermassive types. By finding and studying them, astronomers can fill in the evolutionary gap and understand how black holes grow over cosmic time. One of the most striking insights comes from JWST's ability to observe galactic centers with exquisite detail. In many galaxies, including merging ones, black holes are seen interacting with their environments, driving massive jets of energy, influencing star formation, and sculpting the structure of their host galaxies. This relationship, once only theorized, is now being observed. JWST shows how black holes and galaxies grow together, in a kind of cosmic dance, each shaping the other. In one observation, Webb peered into a distant galaxy merger where two black holes were on a collision course. Their swirling gravitational fields, immense and invisible, shaped the gas around them into brilliant spirals of glowing dust, captured beautifully in infrared. These mergers, while violent and slow, are responsible for some of the most energetic events in the universe, and they may be common. Webb surveys suggest that galaxy mergers, and by extension black hole mergers, were more frequent in the early universe than previously thought. This implies a universe rich with dynamic interactions and high-speed transformations. Another surprise has been the quiet giants, black holes that aren't actively feeding. While not as luminous as quasars, these dormant black holes can now be studied by JWST via the stars that orbit around them. Their gravitational pull betrays their presence, and infrared spectra help astronomers map their surroundings and determine their mass with newfound accuracy. There is still so much we don't know. What happens at the event horizon? Is information truly lost forever? Could black holes be connected to other parts of the universe through hypothetical wormholes? These remain open questions, some perhaps forever out of reach. But what we do know is this: black holes are not just destructive, they are essential. They shape galaxies, trigger star formation, and may have played a key role in the emergence of life-bearing systems like our own. With the James Webb Space Telescope, we are no longer merely theorizing, we are witnessing, and in doing so, we are drawing back the curtain on one of the universe's most majestic and mysterious actors. Chapter 9. Mapping the hidden web of dark matter. One of the most profound enigmas in modern astrophysics is the existence of dark matter, an invisible substance that does not emit or absorb light, but exerts a gravitational pull, shaping the large-scale structure of the universe. Although it cannot be seen directly, scientists can trace its presence through the behavior of visible matter, especially galaxies. The James Webb Space Telescope, with its exceptional resolution and sensitivity, has provided researchers with an unprecedented opportunity to study how dark matter influences galaxy formation and the universe's structure. By observing the distribution of galaxies across vast distances, JWST helps astronomers map the cosmic web, a vast network of filaments composed of dark matter and galaxies stretching across the cosmos. In one of its remarkable achievements, JWST captured gravitational lensing effects, a phenomenon where the gravity of massive objects like galaxy clusters bends the light from more distant galaxies behind them. These distortions offer direct clues about the location and concentration of dark matter. Through detailed imaging of these lensed galaxies, JWST has allowed scientists to build intricate dark matter maps, tracing its otherwise invisible presence with extraordinary clarity. These maps not only confirm the existence of dark matter, but also help refine our models of how galaxies evolve over time. In areas where dark matter is dense, galaxies tend to cluster and grow. In contrast, regions of low dark matter density are often barren. This pattern provides a deeper understanding of how gravity sculpts the cosmos, guided by an unseen hand. Furthermore, JWST's infrared vision enables astronomers to peer further back in time than ever before. By analyzing ancient light from the early universe, researchers can study the initial conditions that gave rise to dark matter distributions we observe today. This work is essential to testing theoretical models that attempt to explain what dark matter actually is, a question that remains one of the greatest mysteries in science. Although JWST does not detect dark matter directly, its role in mapping and interpreting the structure of the universe brings us closer to understanding this elusive substance. It's as if we are tracing the shadows of something massive and invisible, slowly revealing the threads of a grand cosmic tapestry. Chapter 10: Witnessing Galaxy Mergers in Real Time. In the grand theatre of the cosmos, few events are as dramatic or as beautiful as the collision and merger of galaxies. These cosmic encounters, though unfolding over millions or even billions of years, are key drivers in the evolution of the universe. With the powerful eyes of the James Webb Space Telescope, we can now observe these galactic dances in greater detail than ever before. Using its infrared capabilities, JWST has captured breathtaking images of galaxy mergers at various stages. Some show distant galaxies just beginning to interact, pulled toward each other by gravity, their shapes starting to distort. Others reveal pairs already locked in embrace, their spiral arms twisted and their cores glowing as new stars are born from the chaos. These mergers aren't just spectacular to look at, they're scientifically rich. During these events, clouds of gas and dust collide, triggering intense bursts of star formation known as starbursts. JWST's sensitive instruments can pierce through these dense clouds to observe these newborn stars, allowing astronomers to study how such extreme environments influence stellar birth and evolution. Perhaps even more intriguing is what these mergers reveal about the growth of supermassive black holes. At the heart of many galaxies lies a colossal black hole. When galaxies merge, their central black holes are believed to spiral toward each other, eventually coalescing. JWST helps detect the energetic signatures of this process, as vast amounts of gas are funneled into the black holes, causing them to flare with activity. Beyond the drama, these mergers help scientists understand how galaxies grow and evolve. Many of the massive elliptical galaxies we see today likely formed from such cosmic collisions. By studying mergers at different distances, and therefore different times in the universe's history, JWST allows us to piece together a timeline of galactic development. Thanks to JWST, we are witnessing the creative destruction of galaxies, a process both violent and generative. Each merger reshapes the cosmic landscape, forging new stars, altering galactic structures, and even forming entirely new galaxies. In these silent yet colossal events, the universe continues to remake itself, one merger at a time. Chapter 11: Exploring the Cosmic Cliffs and Celestial Mountains. One of the most captivating images captured by the James Webb Space Telescope reveals a scene that resembles an alien landscape: the cosmic cliffs of the Carina Nebula. These towering walls of gas and dust, glowing with stellar light, are not mountains at all, but immense star-forming regions sculpted by stellar winds and radiation. The Carina Nebula lies about 7,600 light-years away in our own galaxy. With its ability to see in infrared, JWST has peered deep into this massive cloud, uncovering dozens of previously hidden baby stars. Some of these are just beginning their life cycles, still wrapped in their natal cocoons of gas. Before Webb, many of these regions were veiled in mystery. Visible light couldn't penetrate the dense clouds of dust. But Webb's infrared vision has changed that. It reveals how radiation from nearby massive stars erodes the surrounding gas, carving out cavities and creating pillars and ridges. This interaction shapes the environment for future star formation and may even determine how planetary systems emerge. The cosmic cliffs are more than just beautiful. They are natural laboratories, allowing scientists to study how stars ignite and evolve under extreme conditions. These regions offer crucial clues to the early stages of solar systems, possibly similar to how our own sun and planets once formed. Beyond Carina, JWST has also turned its gaze to other celestial landscapes, like the Eagle Nebula and the Pillars of Creation. These iconic regions have now been seen in unprecedented detail, with every tendril of gas and every new star emerging more clearly than ever before. With each new image, JWST reveals not just the aesthetic grandeur of the universe, but also the processes that govern its structure and evolution. These cliffs and peaks of light and shadow are monuments of cosmic history, silent witnesses to the birth of stars, planets, and perhaps life itself. In the vastness of space, JWST brings us closer to the wonders of our own galactic backyard, reminding us that even in the most distant reaches of the cosmos, there is beauty, order, and constant transformation. Chapter 12. The Hidden Chemistry of the Universe. Beyond the dazzling visuals of distant galaxies and glowing nebulae, the James Webb Space Telescope offers something perhaps even more profound: a deeper look into the chemistry of the cosmos. Through its powerful instruments, especially its spectrographs, JWST is able to break down light into its component wavelengths, revealing the unique chemical fingerprints of celestial objects. This process, called spectroscopy, allows scientists to detect the presence of elements and molecules, even in galaxies billions of light-years away. One of JWST's most exciting discoveries involves the detection of complex organic molecules in places where we least expected them, like the atmospheres of exoplanets or the dusty regions around newborn stars. These molecules include methane, carbon dioxide, water vapor, and sulfur dioxide, all of which play key roles in the chemistry of life. For instance, in the atmosphere of the exoplanet WASP-39b, JWST identified sulfur dioxide, a molecule created by photochemical reactions, indicating that the planet's atmosphere is being shaped by its star's light in real time. This was the first time such a molecule had ever been detected on a planet outside our solar system. In dusty protostellar clouds, JWST has revealed the presence of icy compounds, including frozen carbon dioxide, methane, and ammonia. These ices are believed to be some of the building blocks of life, and their presence supports the idea that the ingredients for biology may be common in the universe. By analyzing the light from galaxies at different stages of evolution, Webb is also helping. Scientists understand how heavy elements like oxygen, carbon, and iron were formed and distributed throughout the cosmos. These elements are forged in the hearts of stars and dispersed by supernovae, giving birth to future generations of stars and planets. Each spectroscopic discovery is like uncovering a hidden message, one that tells us not just what the universe looks like, but what it's made of. The universe is a grand chemical laboratory, and with the JWST, we are finally able to read the recipes written in starlight. In the silent glow of distant worlds and glowing gas clouds, chemistry becomes poetry, and every element speaks of a story, of formation, transformation, and perhaps even life. Chapter 13. Dust, Shadows, and the Architecture of Galaxies. In the vast stretches of the cosmos, not everything that matters shines. Much of the universe is hidden behind veils of cosmic dust, tiny particles of rock and carbon that drift between stars and galaxies. For centuries, these dusty regions have concealed the deeper structures of the universe. The James Webb Space Telescope, however, is designed to peer through these shadows. Thanks to its infrared vision, JWST can penetrate cosmic dust clouds, revealing the complex skeletons of galaxies. It shows us where stars are born, where they gather, and how galaxies evolve over billions of years. What once appeared as faint smudges through earlier telescopes are now revealed as intricate webs of gas, dust, and glowing stars. One of the most stunning examples is JWST's imaging of the Cartwheel Galaxy, a ring-shaped galaxy in the midst of a violent collision with another. Where Hubble saw only fragments, JWST unveiled the dust lanes, the rings of active star formation, and the galactic core, providing a time-lapse of cosmic architecture sculpted by gravity. In the Pillars of Creation, a region inside the Eagle Nebula, the telescope has uncovered fine structures made of dense dust and gas, forming stellar cocoons. These are the nurseries where new stars are forming, shielded from view in visible light, but glowing brightly in infrared. Dust, once considered an obstacle, is now one of JWST's richest sources of information. In nearby galaxies, the telescope traces the dusty spiral arms where young stars light up like embers within swirling currents. In distant galaxies, it sees how dust shapes the formation of stars and planets, playing a key role in the cycle of creation and destruction that drives galactic evolution. The telescope also reveals dust-rich galaxies from the early universe. Massive structures already mature only a few 100 million years after the Big Bang. This challenges long-held assumptions, forcing astronomers to rethink how fast galaxies formed and evolved. In JWST's images, dust is no longer silent or hidden. It speaks in delicate filaments and glowing bands, whispering stories of birth, collision, and cosmic growth. It turns out, even in the darkness, there's a pattern, there's a purpose, and there is beauty, mapped out in the quiet trails of stardust, scattered across time. Chapter 14. The Cosmic Clocks. Measuring time through light. In the universe, time doesn't tick on a watch, it shines through light. The farther we look, the older the light we see. Every photon that reaches us from a distant star or galaxy is a time capsule, carrying the story of where it came from. And the James Webb Space Telescope has become the most sensitive timepiece ever built, able to measure the passage of cosmic time through light. One of JWST's primary missions is to observe the earliest galaxies, those that formed just a few 100 million years after the Big Bang. These ancient galaxies appear faint and red, their light stretched by the expanding universe. This phenomenon is known as redshift, and JWST's instruments are tuned precisely to detect it. With redshift data, scientists can date the age of galaxies, estimate their distance, and reconstruct a timeline of cosmic events. This allows astronomers to trace back the formation of structure in the universe, when galaxies first clustered together, when the first stars ignited, and how everything evolved into the grand architecture we see today. In one of its most remarkable feats, JWST observed Glass C13, one of the most distant galaxies ever seen, formed only about 300 million years after the Big Bang. It's not just a smudge of light. JWST can resolve its shape, composition, and star-forming activity. These ancient snapshots provide crucial clues to how quickly the first galaxies assembled and what ingredients were present at the beginning of cosmic history. But the telescope's timekeeping goes even further. By analyzing the chemical fingerprints in the light from stars and galaxies, JWST can determine how enriched these systems are with heavy elements, those formed through supernovae and stellar fusion. This helps us understand the metallicity of early stars and the generational story of stellar evolution, from pristine hydrogen to complex chemistry. In stellar clusters, JWST can distinguish old stars from young ones, mapping the age structure of star groups within the Milky Way and beyond. This provides a deeper understanding of galactic archaeology, how layers of stellar populations build up over time. And in some of the telescope's most poetic images, we see light echoes, reflections of ancient supernovae bouncing off dust clouds, reaching us long after the star itself exploded. These delayed signals are cosmic ghosts, reminding us that time in the universe flows not in a straight line, but in ripples, loops, and reflections. Thanks to JWST, the cosmos has revealed its inner clockwork. It's a universe not only of space, but of memory, a place where the past lives on, encoded in light, waiting to be read. Chapter 15, Mapping the Invisible, the Dark Matter. Puzzle in the grand design of the cosmos. What we see is only a fraction of what exists. The stars, planets, and galaxies, everything that shines, make up less than 5% of the total content of the universe. The rest is invisible. And one of the most mysterious components of this invisible universe is dark matter. Dark matter doesn't emit or reflect light. We can't see it directly. Yet, its gravitational pull shapes the cosmos on the largest scales. It's what keeps galaxies from flying apart, what forms the scaffolding for cosmic structure, and what guided the earliest formations of matter after the Big Bang. Before the James Webb Space Telescope, our view of dark matter was largely theoretical, inferred presence detected only through its gravitational effects. But with JWST's unprecedented resolution and sensitivity, astronomers are beginning to map its influence more precisely than ever before. Using gravitational lensing, JWST captures the distortions of light caused by massive clumps of dark matter. When the light from distant galaxies travels through a region of space filled with invisible mass, it bends, creating arcs, rings, and warped shapes. These visual fingerprints allow scientists to trace the distribution of dark matter, even though it cannot be seen. JWST's observations of galaxy clusters, such as SMACS 0723, reveal how dark matter pools and how it interacts with visible matter. These insights help cosmologists refine their models of cosmic evolution, testing theories about how structure in the universe emerged over billions of years. More intriguingly, JWST allows researchers to study the formation of early galaxies in dark matter halos. These halos act like invisible cocoons, drawing in gas and dust and enabling stars to form within them. By capturing these early phases of galaxy assembly, JWST is showing us how dark matter isn't just a background force. It's a creative agent in the cosmic story. Even in the outskirts of galaxies, JWST can detect how stars move, subtly influenced by the gravity of surrounding dark matter. These movements reveal the massive halos of dark matter extending far beyond what we can see. Perhaps most exciting is JWST's potential to challenge or confirm new theories. Some scientists propose that dark matter might interact with itself or with normal matter in unknown ways. JWST's data could offer the first clues to these exotic behaviors. Clues hidden in the shapes of galaxies, the timing of their growth, or the clustering patterns in the distant universe. We still don't know what dark matter is. It might be particles yet to be discovered, or something entirely unexpected. But with JWST, the invisible becomes traceable. We are mapping shadows with light, and slowly, the darkness is revealing its form. In this chapter of cosmic discovery, JWST reminds us, even what cannot be seen still leaves a mark. And in reading those marks, we move one step closer to understanding the true fabric of the universe. Chapter 16. The Chemical Recipes of Distant Worlds. The search for life beyond Earth has always begun with a question. What is out there, and what is it made of? For decades, astronomers could only guess the chemical makeup of planets beyond our solar system. But the James Webb Space Telescope is changing everything, bringing us detailed chemical fingerprints from worlds light years away. With its advanced infrared instruments, JWST can analyze the atmospheres of exoplanets as they pass in front of their host stars. This technique, called transit spectroscopy, allows scientists to detect how starlight filters through the planet's atmosphere, revealing the specific molecules that are present. For the first time, we are seeing detailed spectra from exoplanet atmospheres, data that tell us whether a planet holds water vapor, methane, carbon dioxide, or even more complex compounds. These ingredients are essential for assessing a world's potential habitability. In just the first few months of operation, JWST delivered groundbreaking results. One of the most remarkable was the detection of carbon dioxide in the atmosphere of WSP-39b, a hot gas giant about 700 light-years from Earth. This was the first unambiguous detection of CO2 in an exoplanet atmosphere, confirming theories and expanding our chemical toolset for future exploration. But the surprises didn't stop there. WST also observed WSP-96b, another gas giant, and found clear signs of water vapor, not oceans, but clouds high in the planet's atmosphere, glimmering with moisture. Even though WSP-96b is too hot to host life, the ability to detect water so clearly is a stunning demonstration of JWST's power, and a promise for what we, may find on smaller, more temperate planets in the future. What makes JWST revolutionary is not only that it detects chemicals, but that it does so with extraordinary clarity and range. It can pick up tiny variations in the light spectrum, revealing temperature, pressure, cloud layers, and wind patterns. Each of these variables contributes to a planet's overall environment. Some observations go even further. In systems like TRAPPIST-1, where Earth-sized planets orbit a cool red star, JWST is now scanning the atmospheres of rocky exoplanets, a task that has eluded telescopes for years. If these planets hold any signs of biosignatures, the chemical signs of life, they may first appear in JWST's data. And yet, even when planets don't host life, they still have stories to tell. The variety of planetary atmospheres seen so far is astonishing. Metal-rich skies, sodium-filled clouds, and heat-shielding hazes that block sunlight. Every observation is a window into a different version of planetary evolution. JWST is helping to assemble the Cosmic Recipe Book, a catalogue of atmospheres and climates that expands our understanding of what planets can be and what ingredients make them friendly or hostile to life. As this golden mirror peers across the stars, it isn't just searching for Earth's twin. It is telling us what is possible. And in doing so, it brings us closer to answering the most profound question of all: are we alone? Chapter 17. Tracing the origins of water. In the universe, water is essential for life as we know it. From the oceans of Earth to the icy moons of the outer solar system, water connects us to the broader cosmos. But where did this water come from? How did it form in the first place? These questions have long puzzled astronomers. And now, thanks to the James Webb Space Telescope, we are beginning to uncover the answers. One of JWST's most exciting achievements has been its ability to detect water molecules in distant parts of the universe, even in the most unlikely places, like the swirling disks of dust and gas around young, forming stars. These protoplanetary disks are the birthplaces of planets, and with its infrared eyes, JWST has captured clear signs of water vapor within them. This discovery suggests that water forms very early in the planetary formation process, long before planets are fully shaped. In a recent observation, JWST focused on a system called PDS-70, a young star about 370 light-years away. There, the telescope detected warm water vapor in the inner disk, precisely where rocky planets like Earth would eventually form. This is crucial. It means that water isn't something delivered later by comets or asteroids alone. It might already be woven into the fabric of newborn planets. Even more impressively, JWST has identified water in galaxies more than 12 billion light-years away. That's water forming when the universe was less than 2 billion years old. These are some of the earliest water signatures ever observed, pushing back the cosmic clock and reshaping our understanding of how and when the essential elements of life emerged. But how does JWST detect something so subtle as water in a galaxy that far away? It all comes down to light. Water molecules absorb and emit infrared light at specific wavelengths. JWST's instruments are calibrated to these fingerprints, allowing it to detect water even when it's hidden among other gases or trapped within clouds of cosmic dust. These detections are more than chemical trivia. they offer a new cosmic perspective. They tell us that water is not rare or isolated, but rather widespread and ancient, present in a multitude of environments across time and space. This revelation has profound implications. If water is this abundant in the universe, then the ingredients for life might be common too. Every time JWST finds water in a new place, in a distant galaxy, around a forming star, or within the clouds of an exoplanet, it strengthens the possibility that life may have emerged elsewhere, and even beyond the search for life. These discoveries help explain our own origins. The water in our oceans, in our bodies, and in every living cell may trace back to interstellar clouds formed billions of years ago. Clouds that the James Webb Space Telescope is only now beginning to observe directly. In tracing water's cosmic journey, JWST is not just telling us how planets are made. It's revealing how the chemistry of life begins. Chapter 18. The Ghost Galaxies, Revealing the Invisible. In the vast theatre of the cosmos, not everything shines brightly. Some of the most intriguing structures in the universe are those that elude even the most sensitive telescopes. Ghost galaxies so faint and diffuse that they seem to vanish into the blackness of space. But now, thanks to the unprecedented sensitivity of the James Webb Space Telescope, these hidden giants are finally coming into view. Astronomers have long theorized the existence of ultra-diffuse galaxies, enormous collections of stars with very little visible matter. Some are as wide as the Milky Way, yet contain just a fraction of its stars. They're like vast cosmic whispers, barely clinging to form, scattered thinly across space. These ghost galaxies have posed a puzzle. How do such massive structures survive the chaotic forces of galactic formation? Why don't they collapse or vanish altogether? What keeps them together? JWST's deep field imaging has uncovered several of these mysterious galaxies. By peering into dense galaxy clusters, it has spotted faint, extended glows that no other telescope could confirm. These are the signatures of ghost galaxies, nearly invisible to previous observatories, but suddenly illuminated under Webb's infrared gaze. In some cases, JWST has even detected individual stars within them, as well as globular clusters, tightly bound groups of stars orbiting their sparse galactic hosts. These findings help scientists understand how such galaxies evolve and survive despite their fragility. Even more fascinating, some ghost galaxies appear to be rich in dark matter, while others seem to have almost none. One galaxy, designated DF2, shocked astronomers when earlier data suggested it might be devoid of dark matter entirely. JWST's high-resolution follow-up observations are now helping settle that debate by revealing the true motions of its stars, shedding light on the galaxy's mass and structure. This opens the door to new questions. Are there multiple types of ghost galaxies? Could they form in different ways? Some through mergers, others from failed starbursts or stripped material. These faint giants also have a role to play in the cosmic balance of matter. If they're more common than we thought, they might account for a larger portion of the universe's mass than previously assumed. Webb's ability to see them clearly is reshaping our maps of large-scale cosmic structures. Perhaps most eerie of all is their appearance. Images captured by JWST show ghost galaxies as soft, cloudy patches of starlight, without dense cores, without clear arms, and often without much definition at all. They look like memories of galaxies, as if sketched in stardust and left to drift. In the quiet study of these vanishing giants, JWST reminds us that not all of the universe is brilliant and loud. Some of its deepest secrets lie in the faintest echoes, in the places where darkness dominates and light barely lingers. Through these ghostly shapes, we glimpse an unseen universe, one that stretches far beyond the stars we know, silent, hidden, and newly revealed by the power of a telescope that sees the invisible. Chapter 19: Cosmic Clocks. Measuring time with ancient light time in the universe flows in light. Every photon that reaches us from deep space is a messenger from the past, a tiny packet of energy that has crossed the gulf of time to carry a story. With the James Webb Space Telescope, we are not merely observing distant objects. We are peering into the ancient clockwork of the cosmos, measuring epochs, and decoding the rhythm of creation itself. One of JWST's most profound capabilities lies in its ability to see ancient galaxies as they appeared billions of years ago. Because light takes time to travel, the farther we look, the further back in time we see. This is known as look-back time, and JWST extends our gaze deeper into it than ever before. Some of the galaxies JWST has imaged are more than 13 billion years old, dating to just a few 100 million years after the Big Bang. These snapshots allow astronomers to build a timeline, a sort of cosmic census, showing how galaxies grew, evolved, and interacted in the earliest epochs. But JWST doesn't stop there. It also helps refine our measurements of cosmic expansion by observing Type Ia supernovae, the bright standard candles of the universe. Webb helps scientists calculate how fast the universe is stretching over time. These measurements are key to understanding dark energy, the mysterious force accelerating this expansion. Even the chemical fingerprints in JWST's spectra function like time markers. By studying the elemental composition of distant galaxies, astronomers can determine how many generations of stars have lived and died there. The presence of heavier elements like carbon, oxygen, and iron tells us that the galaxy has undergone stellar recycling, and thus it must be older. In a sense, JWST is giving us the universe's diary, page by page. Each image, each spectrum is a timestamp, offering evidence for the age, composition, and motion of celestial bodies. One particularly striking result comes from JWST's observations of ancient quasars, hyperactive galactic cores powered by supermassive black holes. These objects, which blaze with the energy of billions of suns, have been spotted at times when the universe was still in its infancy. Their very existence raises questions. How could black holes grow so fast in such a short cosmic window? Are we missing parts of the timeline? This line of inquiry is reshaping our understanding of cosmic chronology. Time, we are learning, is not only a background dimension, it's something the universe writes into every atom and photon. And then there's the question of our own place in this timeline. JWST's data allows us to trace the lineage of elements that make up our bodies: carbon from ancient stars, iron from supernovae, hydrogen from the Big Bang. In a very real sense, We are part of this cosmic clock, a product of time sculpted by gravity and light. Through JWST, we are no longer passive observers. We are time travelers of thought, walking backward along the thread of history into the starry corridors of beginnings. As each new image is decoded, the hands of the universe's clock tick forward, and yet we move further into its past, seeking not only the origin of stars and galaxies, but the deep pulse of time itself. Chapter 20: Echoes of Creation. Tracing the Big Bang's afterglow. In the vast silence of space, there is an ancient whisper, a soft murmur of heat and light left behind from the birth of everything we know. This lingering afterglow, known as the cosmic microwave background, CMB, is the oldest light in the universe. While the James Webb Space Telescope doesn't observe the CMB directly like some earlier missions did, it plays a powerful supporting role, exploring the universe just after that first light faded, unlocking the chapters that follow the opening lines of creation. ST allows astronomers to examine the cosmic Dark Ages, a time after the Big Bang when the universe was filled with hydrogen, but no stars had yet formed. This era, once invisible to us, is now being illuminated by Webb's infrared eyes. It captures the formation of the very first galaxies, the lights that pierced the dark and began shaping the cosmos as we see it today. By studying these early structures, JWST helps fill the gap between the CMB and the galaxies we're familiar with. It's like connecting the glowing embers of a fire to the roaring blaze that follows. One of JWST's greatest strengths is its ability to detect red-shifted light, the stretching of light as it travels through expanding space. The farther away an object is, the more its light shifts towards the red end of the spectrum. JWST can detect objects so far away that their light has taken over 13 billion years to reach us, meaning they formed shortly after the Big Bang. Through these observations, scientists are refining their models of cosmic inflation, the brief period of explosive expansion that occurred just after the universe's birth. Tiny fluctuations in density during that time would later become the seeds of galaxies, and JWST is now revealing those seeds in bloom. But there's more. The telescope also probes the Ryanization era, a time when the first stars and galaxies emitted enough energy to ionize the hydrogen gas around them, making the universe transparent to light. This epoch, which occurred between 400 million and 1 billion years after the Big Bang, is now observable thanks to JWST's sensitivity. By detecting faint galaxies from this time, Webb helps scientists understand how and when this major transformation occurred and what kinds of objects were responsible. The echoes of the Big Bang are not just background radiation. They're the tapestry of time into which everything is woven. Every star that shines, every galaxy that spins, every planet that orbits is part of that evolving story. And remarkably, JWST's discoveries may even reshape our understanding of the Big Bang itself. Some galaxies it has revealed appear to be more mature than expected, suggesting that structure may have formed faster than current models predict. Could this mean our understanding of the early universe is incomplete? Are there hidden forces or forgotten moments in that first explosion? of light, these questions don't threaten the idea of a beginning, they enrich it. The Big Bang is no longer just a singular event, but a cosmic overture with echoes that JWST is still tracing, across space, across time. With each new observation, we draw closer to understanding how it all began, and what that beginning truly means. Chapter 21: Dark Galaxies. The hidden architects of the cosmos. Among the many mysteries the universe holds, few are as elusive and puzzling as the concept of dark galaxies. Structures believed to exist without the brilliance of stars, shrouded in darkness, made mostly of gas and dark matter. For decades their existence remained theoretical, a whisper in cosmological models. But now, with the James Webb Space Telescope, we're inching closer to unveiling these ghostly architects of the cosmos. Dark galaxies are thought to be the earliest building blocks of the universe. Galactic shells that, for reasons still unclear, never ignited the spark of star formation. These galaxies contain enormous amounts of gas, the raw material for stars, yet seem eerily dormant. If they do exist, they could offer vital clues to the processes that shaped galaxies as we know them. The challenge? They emit little or no visible light, making them practically invisible to traditional telescopes. But JWST, with its infrared vision, is designed precisely for this kind of challenge. Infrared light allows astronomers to detect the faint heat signatures of objects that are cold, hidden, or far away. By focusing on the subtle emissions from cold gas and dust, JWST can help identify galactic structures that have not yet formed stars, or that contain mostly non-luminous matter. Recent observations using Webb's powerful instruments have started to suggest anomalies, massive clouds of gas, where we would expect to see star formation, but don't. These may very well be the first glimpses of dark galaxies, captured in the earliest stages of cosmic history. But what could keep a galaxy from forming stars? One possibility is low metallicity, meaning the gas within is too pristine, lacking the heavier elements needed to cool and collapse into stars. Another theory suggests that intense radiation from nearby young galaxies could suppress star formation in their neighbors, leaving them in a suspended starless state. There's also a deeper mystery. Dark galaxies could be dark matter-dominated halos, massive clumps of invisible matter that pull in gas but never become luminous. If JWST can map these halos using gravitational effects or subtle gas emissions, it would provide direct evidence of dark matter's structure on galactic scales. Understanding dark galaxies may also help solve a long-standing problem in cosmology, the missing satellite problem. Simulations predict that there should be many more small galaxies orbiting large ones than we currently observe. Dark galaxies could be the missing population, invisible satellites hiding in plain sight. As Webb continues to scan the sky, astronomers are developing new techniques to search for these hidden giants. By looking at how light from distant galaxies is absorbed by intervening gas, or by detecting Rayonization-era fluctuations, they hope to piece together a map of these dark architects. The pursuit of dark galaxies is more than just a search for shadows. It's a quest to understand the scaffolding of the universe, the silent framework upon which luminous galaxies later formed. And in that darkness, we may find the key to one of the universe's deepest secrets: how structure emerged from chaos and how invisible matter continues to shape the visible world. Chapter 22: Listening to the Cosmos, Gravitational Waves and the Role of JWST. The Great Silence of Space, a new way of hearing the universe has emerged. Gravitational waves. These are ripples in space-time, first predicted by Albert Einstein over a century ago, but only directly detected in 2015 by the LIGO Observatory. Since then, they've opened an entirely new window into cosmic events, from colliding black holes to neutron star mergers. And while JWST wasn't built to detect gravitational waves directly, it plays a crucial role in understanding the aftermath of these extraordinary cosmic phenomena. Gravitational waves are generated by the most cataclysmic events in the universe. When massive bodies like black holes or neutron stars spiral into each other and merge, these events send out waves through the fabric of space-time itself, traveling across the cosmos at the speed of light. But what happens after the wave passes? That's where the James Webb Space Telescope steps in. JWST can visually observe the light echoes or electromagnetic counterparts of gravitational wave events. For example, when two neutron stars collide, the explosion, known as a kilonova, emits not just gravitational waves, but also a brilliant burst of radiation. Webb's powerful infrared instruments can capture this light long after the explosion fades from optical view. These kilonovae are of special interest because they're believed to be factories of heavy elements like gold, platinum, and uranium. For years, scientists debated where these elements were created. Thanks to observations coordinated between gravitational wave detectors and telescopes like JWST, we now have strong evidence that these stellar collisions forged the universe's rarest materials. When gravitational wave observatories alert astronomers to a new event, JWST can be rapidly repositioned to observe the location, even if it's extremely faint or distant. This rapid response capability allows it to study the light curves, chemical signatures, and debris clouds from these explosive moments in cosmic history. One of JWST's key strengths in this area is its ability to detect infrared emissions that emerge as the dust and debris from these events cool and expand. Unlike visible light, which may fade quickly or be blocked by dust, infrared radiation continues to shine, giving scientists an extended window to study the aftermath. This coordination between different types of observatories, gravitational, wave detectors on Earth, and JWST in space, marks the rise of multi-messenger astronomy. It's a collaborative approach that brings together data from different messengers of the universe: light, gravity, particles, and more. Through this combined lens, we gain a more complete picture of cosmic events, not just their light, but their movement, mass, energy, and composition. Looking ahead, as gravitational wave detectors become even more sensitive and JWST continues its journey among the stars, this partnership promises to unravel the secrets of the most violent and mysterious objects in the universe. In this quiet listening, where gravity whispers and stars burst into gold, we're learning to understand the rhythm of the cosmos, not just with our eyes, but with every tool at our disposal. Chapter 23: The Cosmic Web. Mapping the large-scale structure of the universe. The universe is not a random scattering of stars and galaxies. It has structure, an immense and interconnected architecture known as the cosmic web. This vast network of filaments, clusters and voids stretches across billions of light years, forming the skeleton of the cosmos itself. With its unmatched infrared vision, the James Webb Space Telescope, JWST, is helping scientists uncover this colossal framework in unprecedented detail. The cosmic web is composed of dark matter, gas and galaxies, all linked together by the invisible threads of gravity. Where these threads intersect, galaxies form in clusters and superclusters, like luminous beads strung along cosmic strings. In the spaces between, called voids, there are far fewer galaxies, creating a bubble-like pattern that only becomes visible on the largest possible scales. Before JWST, astronomers had hints of this structure from simulations and wide-field surveys. But now, with Webb's ability to observe faint ancient galaxies in the early universe, we're getting a direct look at how this structure emerged. By peering deeper into the cosmos and further back in time, JWST allows scientists to study how galaxies formed and aligned along the filaments of the cosmic web just a few 100 million years after the Big Bang. These observations offer insights into how dark matter sculpted the universe, even though we cannot see it directly. One of the telescope's groundbreaking capabilities is detecting the spectral fingerprints of hydrogen gas, the most abundant element in the universe. Hydrogen tends to gather along the filaments of the cosmic web, and Webb can trace its distribution by capturing the Lyman alpha emissions from distant galaxies. These emissions reveal the density and temperature of the gas, helping to build three-dimensional maps of the Webb's structure. In a recent JWST survey, astronomers observed a group of distant galaxies that appear to be aligned along a massive filament, more than 3 million light-years long. This is one of the earliest and most detailed views of cosmic web formation in action, a powerful confirmation of decades of theoretical models. Another exciting application is the study of cosmic voids, the vast empty spaces between filaments. JWST's deep sky imaging can detect the faint galaxies that dwell in these lonely regions, helping astronomers understand how matter is distributed even in the universe's most desolate corners. The importance of these findings lies in their contribution to cosmology, the science of the universe's origin, evolution, and fate. By understanding the layout of the cosmic web, scientists can refine their models of how the universe expanded and grew under the influence of dark matter and dark energy. Furthermore, the large-scale structure of the cosmos may hold clues about the initial conditions of the Big Bang and the subtle quantum fluctuations that seeded the entire web. With JWST acting as a cosmic cartographer, we are beginning to chart the invisible. In essence, Webb is not just taking beautiful pictures of galaxies, it's helping us understand the architecture of everything, from the grandest scales to the smallest details. The cosmic web is the framework that holds the universe together. And as we trace its glowing threads through time and space, guided by the keen eye of JWST, we come one step closer to grasping the true shape of the cosmos. Chapter 24: The Ghost Light, Intragalactic Glow, and the Search for Orphan Stars. In the silent spaces between galaxies, where darkness seems complete, a faint glow lingers, Soft, ethereal, and almost invisible, this is the intragalactic light, often called ghost light, a diffuse luminescence emitted by orphan stars, those that no longer belong to any galaxy. With the precision of its infrared instruments, the James Webb Space Telescope, JWST, has begun detecting and analyzing this elusive light, offering new clues about how galaxies evolve, interact, and sometimes collide. These orphan stars are the wandering souls of the universe. They once lived within galaxies, formed in the cradles of stellar nurseries, and burned brightly alongside billions of siblings. But through cosmic events, galactic mergers, tidal forces and gravitational disruptions, they were thrown from their homes, left to drift through the vast darkness between galactic systems. Before JWST, detecting this faint light was nearly impossible. The glow is so diffuse that even powerful telescopes like Hubble struggled to capture it clearly. But Webb's incredible sensitivity in the infrared allows it to separate this soft emission from background noise, revealing the structure and extent of these mysterious stellar castaways. One recent JWST study observed a massive cluster of galaxies, uncovering a shimmering fog of intragalactic light. This faint halo is made up of stars torn from their galaxies over billions of years. By studying the color and composition of this light, scientists can determine the ages, metallicities, and motion of these orphan stars, and, in doing so, learn about the violent histories of their parent galaxies. The patterns of intragalactic light also offer a new way to trace dark matter. Because these stars are influenced by gravitational forces alone, their distribution follows the shape of dark matter halos, which are otherwise invisible. Mapping the ghost light is like mapping the invisible hand that sculpts galaxy clusters. But the implications reach beyond structure and violence. These rogue stars might host planets, lonely worlds adrift in intergalactic space. It's a haunting thought, a planet orbiting a star with no galaxy, no sunrises, and no nearby stars to light its sky. JWST's observations also suggest that the amount of intragalactic light might be greater than expected. This could mean that galactic interactions, especially in the early universe, were more frequent or more violent than previously thought. Galaxies were not peaceful island universes, but active, shifting structures, constantly reshaped by their neighbors. In this way, JWST transforms what once seemed like cosmic leftovers into critical clues. The ghost light tells a story not of the forgotten, but of the forces that built the universe. One collision, one ejected star, and one lost world at a time. In the silence between galaxies, where no one expected to find anything, Webb has found a quiet whisper. The gentle light of stars without a home, still shining, still telling their tale. Chapter 25. Ancient Chemistry. Unveiling the oldest molecules in the universe. The James Webb Space Telescope doesn't just see stars and galaxies, it deciphers the very chemistry of the cosmos, peeling back layers of time to reveal the molecules that formed in the universe's earliest epochs. One of its most remarkable feats has been detecting and analyzing ancient molecules, some dating back more than 13 billion years, offering a chemical narrative of the infant universe. In its quest to understand how matter evolved after the Big Bang, JWST targets the faint glow of primordial galaxies. Within this light, buried in the infrared spectrum, lie the subtle chemical fingerprints of elements and molecules: carbon, oxygen, hydrogen, water vapor, methane, and more. These are the building blocks of stars, planets, and eventually, life. Recently, JWST captured a spectrum from a distant galaxy named JWST Z13-0, believed to have formed just 300 million years after the Big Bang. Within this infant galaxy, Webb detected the presence of oxygen, a molecule that should have taken hundreds of millions of years to form in significant quantities. Its early presence suggests that star formation in the early universe was not only happening sooner than we thought, but was incredibly efficient, creating heavier elements in cosmic record time. This challenges long-held beliefs that the early universe was chemically simple. Instead, JWST shows that galactic chemical enrichment may have happened rapidly, meaning stars lived and died quickly, seeding space with complex elements through supernova explosions. In other observations, JWST has examined protoplanetary disks, the dusty, swirling structures surrounding young stars. These are the birthplaces of planets. Within these disks, JWST found water vapor, carbon dioxide, and organic molecules, even in systems just a few million years old. It's an extraordinary insight into how fast chemistry works on the cosmic scale, and how the potential for life might have arisen earlier than imagined. JWST has also uncovered traces of carbon-bearing molecules in distant galaxies. These molecules are crucial for organic chemistry and life as we know it. The discovery of such complexity in the early universe stirs exciting questions. Could primitive life, or its ingredients, have begun much sooner than we expected? Moreover, the telescope's ability to analyze molecular hydrogen, J2, the JWST most abundant molecule in the universe, is helping astronomers understand how cold gas collapses to form stars. These observations allow us to reconstruct the chemical environment of galaxies when the universe was just a few % of its current age. The revelations go beyond raw data. They reshape our cosmic origin story, adding rich chemical texture to what was once seen as a universe of just light and gravity. Webb has become a cosmic archaeologist, uncovering the molecular fossils of a bygone era. With every observation, it tells us the universe was never truly simple, not even at its dawn. Chapter 26: Echoes of the Big Bang. Tracing cosmic backgrounds and early structures. While the James Webb Space Telescope does not directly observe the cosmic microwave background, that ancient glow left over from the Big Bang, its infrared eyes allow it to trace the structures and patterns that emerged from those early echoes. In this way, JWST continues the work of cosmic archaeology by mapping the formative moments of the universe, when matter first began to organize itself into stars, galaxies, and clusters. The cosmic microwave background, CMB, first discovered in 1965, provides a snapshot of the universe when it was just 380,000 years old, a time when light could finally travel freely through space. But JWST steps in hundreds of millions of years later, at the point when this light had already seeded the formation of the first galaxies. Webb can now observe the results of the primordial fluctuations in the CMB, regions of slightly different density that eventually grew into the cosmic web of matter. With its powerful instruments, JWST has started identifying the oldest known galaxies, some of which formed less than 300 million years after the Big Bang. These early galaxies are key to understanding how the small variations in the CMB evolved into large-scale cosmic structures. They also allow scientists to test and refine cosmological models, including those dealing with dark matter and cosmic inflation. In one landmark observation, Webb focused on a patch of sky that appeared nearly empty. Yet, when its deep field images were compiled, thousands of faint galaxies emerged, many so distant that their light had traveled over 13 billion years to reach us. These galaxies provide a direct line of sight into the era of reionization, when the universe's first light sources reionized the hydrogen fog that had previously dominated space. ST's spectroscopy also reveals the metal content of early galaxies. This is vital because the Big Bang produced mostly hydrogen and helium, with virtually no heavier elements. The presence of metals in young galaxies means that stellar cycles, birth, life, and death, had already begun, enriching the cosmos with new ingredients. One of the most fascinating outcomes of Webb's deep universe observations is the challenge they pose to standard cosmological timelines. Some galaxies appear to be more massive and structured than models predicted would be possible so soon after the Big Bang. This has sparked debates and renewed efforts to refine our understanding of how quickly matter clumped together to form complex systems. Though it doesn't detect the original Big Bang flash, JWST operates like a cosmic stethoscope, listening to the heartbeat of the early universe through the structures that grew from its initial pulse. Every cluster of stars, every arc of dust and gas whispers secrets from a time when the cosmos was still young and chaotic. Through this lens, Webb brings us closer than ever to the birth of structure, to the moment when the universe began shaping, the scaffolding that would one day hold galaxies, stars, and life. Chapter 27. The Hidden Cosmos. Revealing the invisible universe. Throughout history, much of the universe has remained invisible to our eyes, not because it doesn't exist, but because we lacked the tools to see it. Dust clouds, faint galaxies, and the elusive structures of dark matter all whispered from the shadows. But with the James Webb Space Telescope, we now have a key that unlocks these hidden realms. Unlike visible light, infrared radiation can pierce through cosmic dust. Webb's powerful infrared detectors allow scientists to observe regions of space that once appeared opaque or empty. This capability is crucial in areas like stellar nurseries, where stars are born inside thick clouds of gas and dust. Where other telescopes saw only shadows, JWST reveals glowing tendrils of star-forming material, newborn stars still wrapped in their cradles of dust. In one iconic image, JWST captured the Tarantula Nebula, a chaotic high-energy region teeming with young stars and complex gas formations. What was once obscured is now alive with structure and motion. Scientists can track the early stages of stellar evolution with unprecedented clarity, watching as gravity, heat, and time shape cosmic creation. But Webb's reach goes beyond dust clouds. It can also observe dwarf galaxies and low surface brightness objects, small faint galaxies that are often overlooked. These quiet galaxies, which contain clues about how galaxies evolved over time, are now coming into focus. Some of them may even be primordial galaxies, relatively unchanged since the early universe. Another powerful application is Webb's ability to detect light from cool stars and brown dwarfs, celestial bodies too faint to be studied in detail before. These substellar objects can help bridge the gap between planets and stars, offering insight into both categories. Observing these faint sources expands our understanding of how mass, temperature, and gravity influence formation and evolution. Then there's dark matter, the invisible scaffolding of the universe. Webb can't detect dark matter directly, but by mapping how galaxies cluster and how light is distorted by gravity, a phenomenon called gravitational lensing, it helps astronomers infer where dark matter resides. In massive galaxy clusters, Webb reveals arcs and smudges of light, background galaxies stretched and magnified by gravity. These cosmic lenses provide one of the best indirect methods of studying the invisible. By charting the contours of this unseen realm, JWST pushes astronomy into a new era. It's not just showing us what we couldn't see. It's revealing that the majority of the universe is still waiting to be discovered, hidden in wavelengths and forces that challenge our current tools and understanding. In unveiling the invisible, the James Webb Telescope becomes more than an observatory. It becomes an instrument of wonder, extending our reach into the universe's most secret corners, and inviting us to look again at a cosmos that's far more alive and far more complex than we ever imagined. Chapter 28. A new map of the universe. Charting cosmic structure with WebAIs, we gaze into the vastness of the universe. We often wonder, is there an order to all this? Are galaxies scattered randomly? Or is there a deeper structure hidden across the cosmic tapestry? The James Webb Space Telescope is helping to answer that question by building a new, high-resolution map of the universe's large-scale structure. Our cosmos is not a uniform expanse. It is a web. A cosmic web made of filaments of dark matter, gas, galaxies, and voids stretching across billions of light years. This intricate network forms the backbone of the universe. But understanding its shape and evolution requires seeing deeper, farther, and in greater detail than ever before. Webb's ability to detect faint galaxies from the earliest eras of the universe, as early as 300 million years after the Big Bang, allows astronomers to trace how cosmic structures emerged. By observing galaxies at different stages of their development and mapping their distribution, JWST is providing a clearer picture of how gravity pulled matter into place to form the scaffolding we see today. One of Webb's surprising discoveries is the unexpected maturity of some early galaxies. These galaxies, observed at vast distances, seem more developed and massive than our models predicted. Their presence forces scientists to rethink how quickly cosmic structures formed and how matter organized itself in those early moments. DM also excels at studying galaxy clusters, some of the largest gravitationally bound objects in the universe. By analyzing light bent through gravitational lensing, astronomers can study not only the clusters themselves, but also the more distant galaxies hidden behind them. This method offers a double benefit, probing both nearby structures and the deep universe in one image. In one particularly striking observation, JWST revealed the SMACS 723 field, a galaxy cluster acting as a natural telescope. The cluster's immense mass warped space-time, magnifying and stretching light from background galaxies. This image alone contained thousands of galaxies, some never seen before, arranged like jewels across space and time. Such observations help refine our models of cosmic evolution, showing how galaxies cluster together, how dark matter shapes the universe's layout, and how gas flows between structures to fuel star formation. But perhaps the most profound impact is philosophical. Seeing this interconnected cosmic web reminds us that everything in the universe is linked, from the smallest particles to the largest galactic superclusters. Webb is helping us understand not just what's out there, but how it all fits together. In mapping this architecture of space, the James Webb Space Telescope is more than just a scientific instrument. It's a cartographer of the cosmos, sketching out the grand design of a universe woven with mystery, gravity, and light. Chapter 29. Whispering Shadows. Tracing the invisible threads of dark matter. Everything that shapes our universe can be seen. In fact, the majority of the universe's matter is invisible, not because it's hidden by distance or dust, but because it doesn't emit or reflect any light at all. This mysterious material is called dark matter, and the James Webb Space Telescope is offering new ways to trace its ghostly presence. Dark matter doesn't glow or shine, but it leaves its fingerprints everywhere. It bends light through gravitational lensing. It holds galaxies together despite their rapid spins. It shapes the cosmic web, influencing where galaxies form and how they evolve. And now, thanks to Webb's powerful sensitivity and resolution, astronomers can study these effects with stunning clarity. One of Webb's key contributions to dark matter research is through gravitational lensing. By observing how the light from distant galaxies is warped and magnified by foreground structures, like galaxy clusters, scientists can map the distribution of mass, including dark matter. The distortions Webb captures are subtle, yet they reveal the invisible architecture of the universe. Webb's deep field images, filled with thousands of galaxies, allow researchers to analyze these distortions across vast distances. The result is a more detailed and accurate map of dark matter than ever before, helping us trace how it has shaped the universe from its earliest moments. In some observations, JWST has identified lensing arcs and Einstein rings, elegant phenomena that occur when light from a distant galaxy wraps around a massive object. These structures not only offer breathtaking visuals, but also provide crucial data to understand how dark matter is distributed in space. Webb is also helping to test theories about the nature of dark matter. Some scientists propose that dark matter could interact with itself or behave differently at small scales. By examining how galaxies cluster and move, especially in the early universe, Webb provides new constraints on these theories, pushing the boundaries of what we know. Furthermore, JWST's infrared vision allows it to explore dwarf galaxies and ultra-diffuse galaxies, where the influence of dark matter is especially pronounced. These fragile, faint galaxies are often dominated by dark matter, making them ideal laboratories for studying its behavior in isolation. Despite its name, dark matter may be the key to illuminating the true structure of the universe. And while we still don't know exactly what it is, whether it's a new type of particle or something more exotic, every Webb image, every lensing arc, and every cosmic map brings us closer to unveiling its secrets. In chasing the shadows cast by nothingness, the James Webb Space Telescope reminds us that sometimes the most profound discoveries come not from what we see, but from what we can't. Chapter 30. Echoes from the Beginning. Chasing the First Light. As the James Webb Space Telescope peers deeper into the universe, it also peers further back in time. Light travels at a finite speed, so the photons reaching Webb's mirror today began their journey billions of years ago. In its deepest surveys, Webb captures the first glimmers of starlight, born not long after the Big Bang, the universe's first light. This first light didn't arise instantly. The early universe was hot, dense, and opaque, a cosmic fog of particles and radiation. Only after hundreds of thousands of years did it cool enough for atoms to form, allowing light to travel freely. This event, known as recombination, left behind the cosmic microwave background. But the stars and galaxies we now see in Webb's images took several 100 million more years to form. With its unmatched infrared sensitivity, JWST is uniquely capable of detecting the earliest galaxies, tiny, faint smudges whose light has been stretched by the expansion of space. These galaxies are often smaller, more chaotic and incredibly active, building the first heavy elements and sowing the seeds of structure that would grow into today's cosmic web. In one breathtaking discovery, Webb revealed a galaxy candidate that may have existed just 300 million years after the Big Bang, far earlier than what scientists once believed possible. These findings challenge existing theories of how quickly stars and galaxies formed, suggesting that the early universe may have matured faster and in more complex ways than we thought. But it's not just about galaxies. Webb also studies population. 3 stars, the hypothetical first generation of stars made entirely of hydrogen and helium, without heavier elements, though none have been definitively observed yet. JWST's deep surveys offer our best chance of finding them, or at least their imprints in the earliest galaxies. Beyond individual stars and galaxies, Webb captures the architecture of the early cosmos. Its images reveal filaments and clusters that hint at how matter flowed, collapsed, and built the structures we see today. These observations help us understand how gravity sculpted the universe from nearly featureless beginnings into a grand cosmic web. Through these faint signals, these echoes from the beginning, JWST becomes a time machine, letting us witness the birth of the first light. And in doing so, it offers answers to our oldest questions. How did it all begin? Where did we come from? Each new image from the telescope reminds us that the universe is not a static place, but a story still unfolding, a story that began in fire, evolved in darkness, and now shines across the cosmos, waiting to be discovered. Final chapter, a legacy. Written in light as our journey through the cosmos with the James Webb Space Telescope comes to a close, we are left with a profound sense of wonder. This remarkable observatory, suspended beyond the Moon's orbit, is more than a telescope. It is humanity's extended vision, stretching into the vast silence of space and the deep corridors of time. We've explored the birthplaces of stars hidden within veils of dust, peered into galaxies that lived when the universe was still young, and witnessed the quiet drift of rogue planets in the darkness. We've listened to the silent signals of ancient light, watched black holes sculpt galaxies, and studied distant atmospheres that may one day reveal signs of life. Each discovery, each data point, is more than just science. It's a chapter in our shared cosmic story. The James Webb Space Telescope teaches us that we are not merely observers of the universe, but a part of it. Made of stardust, born from ancient stars, and drawn to the mysteries of the night sky. Though we cannot yet travel to these distant worlds, our curiosity reaches them, and thanks to Webb, the invisible becomes visible, the distant becomes near, and the unknown begins to take shape. As the telescope continues its mission, it will quietly send back images and data, unraveling more secrets, answering more questions, and no doubt raising new ones. Its legacy is just beginning. So, as you drift into rest or reflection, remember, out there, light that began its journey billions of years ago is only now being seen, because we dared to look, and that is a beautiful thing. Good night, explorer of the stars.